We're now here to present you with our analysis and outcome of our DURF project. Our research topic is airfare pricing. We aim to answer the following two questions. The first one, what are the key factors associated with airfare? The second one, how should customers decide when to buy an air ticket? Our methodology includes machine learning and systematic trading. Here is the timeline for our project. From data preparation to machine learning, and in the end, we built a self-designed decision model. Our data is a two-dimensional dataset containing the flight ticket price from 45 days before the takeoff day to the takeoff day of CZ3100 in 2017. As there are many limitations regarding acquiring data of historic airfare price, we choose one airline to be our case study. From the previous dataset, we derived several interesting data. For example, daily price change track, price adjustment direction track. We will explain how we're going to use this data in later parts. Here is a demonstration of price fluctuation. So our two main questions to be answered from the consumer side is, number one, are there any patterns in airfare? Which are the key factors that impact price of the same airline? The second question is, when would be the optimal time to make the purchase? Is it wise to buy immediately or delay the purchase? For the horizontal analysis, we have several potential Y variables, including average price, log average price, and volatility of average price. The average price is calculated by the average of the 45 data points before departure. We plotted the distribution of average price. It is close to normal distribution but slightly skewed to the left. We also plotted the distribution of the other two potential Y variables. After some preliminary analysis, we chose the average price as our Y variable. First of all, it's the most direct approach to solve our research objective. It also has tighter linkage with our chosen X variables. Also, we believe it has higher practical value to consumers as prediction can help choose the optimal time to travel. We have chosen a number of X variables from multiple dimensions. The first dimension is microecon data, which includes stock price, CPI, oil price, and SSE index. The second dimension is date of travel related, which includes day of the week, whether it's weekend, whether it's summer vacation or winter vacation, or whether it's a travel peak in either cities. The last dimension is weather-related variables, which includes air quality of both cities and also RR, which is rainfall, and also temperature of Guangzhou Airport. Before running linear models, we ran a bivariate analysis on all of our continuous X variable, and we discovered high correlation between temperature, air quality GZ, and oil price. So we added interaction terms in our models to avoid multicollinearity. We went on to do a linear regression. After manipulating independent variable combination, the optimal adjusted R-square we can get is 0.27. The most significant independent variables include bullet train, summer vacation, and GZ travel peak. When there's alternative transportation available, the average price is lower. We also did a semi-log model, as some of our X variables are not in the same scale as our Y, and the optimal adjusted R-square we can get is 0.272, which is slightly higher than the linear model. The most significant independent variables are the same as the previous model output. Here is a residual plot of both our models. In addition to linear models, we also built machine learning models to predict airfare price. We created a binary variable, which is average high-low, to simplify analysis. The criterion we set is that price higher than median are classified as high and the rest are classified as low. We split all data points to two sets with a training set of 274 average prices and a validation set of 91 prices. The models we ran include boosted tree, bootstrap forest, and generalized regression. The first machine learning model we built is boosted tree. It has a misclassification rate around 24%. The F week has the highest contribution among all columns. We then went on to do a bootstrap forest model. It has a misclassification rate of 25%, slightly higher than the boosted tree model. Interestingly, profiler of this model suggests that winter and summer vacation have little influence over ticket prices, which is against our common sense. We did a generalized regression with Lasso. Lasso model has a lambda penalty of 0.2, which is really close to 0. We also did elastic net. Both regression models suggest that price is most likely to be high on Friday, and the difference is significant. Among the 4 machine learning models we built, elastic net model has the lowest misclassification rate at 18%, while AUC comparison suggests that Bootstrap Forest model is the best performing model. It has an area under the curve of 0.84. Through our analysis, we see that data and travel-related factors have the highest impact on airfare, while macroecon-related factors have the least impact. Most models in our analysis suggest that the day of the week as the strongest indication of price high-low, and prices are most likely to be above median on Fridays. All models in our analysis have relatively high prediction power and high AUC, while the limitation of our model lies in the limited number of data points available, as we have only included 365 prices. The analysis would have higher practical value if we had access to larger datasets. Thus, we can compare different models for different airlines. For example, if we can compare domestic and international airlines, we can see how different factors have different importance in different types of airlines.
Now let's move to the second part of the analysis. Here the problem we want to solve is when should a customer buy the ticket after he or she made the decision to travel. If we plot a historical price of the 45 period of the air flight, there is a rough trajectory, but with a fair amount of noise. In the following slides, we will explain some intuitive and clear patterns we have found through data visualization, data manipulation, and data analysis. The first and most important observation is the counterintuitive fact that airfare does not necessarily increase as time approaching the takeoff day. This fact actually gives us room to come up with strategies for customers to reduce cost. As you can see on the graph, when we plot out the fluctuations of airfare of CZ3100, the red part represents where airfare decreases as time goes. To better support this argument, using all the data in 2017, we find out that if a person decides to buy an air ticket 30 days before the takeoff day or earlier, there will be a possibility of more than 50% that he or she has a chance to catch a lower price in later periods. To take a closer look at the ups and downs, we find obvious patterns on price rise on specific days. This indicates that customers had better purchase before this red line. The hidden message from this fact is that even if we're willing to delay the purchase to wait for a lower price at some time, it is irrational to wait forever. A limit or stop loss point is necessary. Similarly, if we take price increase as positive 1, price decrease as negative 1, and aggregate all the price changes, we get all negative numbers before 11 days before the takeoff day. It means that more than half of flights during the year adjust their price downwards during this period. The two obvious rises on 9 days and 3 days before the takeoff day also manifest on this graph. In a cumulative sense, the frequency of moving upwards exceeds the frequency of moving downwards at 10 days before the takeoff day. This result is consistent with the previous one. These two graphs gives us a hint that several days are worth paying attention to. They are the break-even points or extreme points. This graph also shows a similar analysis in terms of cumulative price change. We also observed some 45-degree lines on a color-coded price change grid. This phenomenon tells us that some dates might also have significant meanings, and it's just we can't explain them now. This prompts us to carry on further investigation on different strategies associated with different dates through simulation. Based on all the observations demonstrated in previous slides, we come down to this self-designed decision model for customer. First of all, the objective of this model is to explore systematic ways for customers to reduce cost. Then we narrow down all the insights into two bottom lines. One is that one should not always purchase immediately. The other is that some days have specific significance attached to them in terms of making purchase decisions. The baseline model here is just buy the ticket immediately no matter when you decide to buy it. The experimental model implements the following strategy. Wait until next low price if it's still before minus X day unless hitting the loss control limit. Otherwise, buy immediately. Here, minus X means X day before the takeoff day. X can be any integer from 1 to 45. The first type of strategy is shown in this illustration. We set a threshold in the middle. Before this threshold, we recommend customers to delay the purchase in order to catch the next lower price. After this threshold, we recommend customers to buy as soon as possible. We varied the value of X and got simulation results. The second type of strategy imposes a stop-loss point on top of the first type. And we set this stop-loss point to 100, 200, 300, 400, and 500 RMB. The third type of strategy imposes a wait time limit on top of the first type, and we set this wait times to 3, 7, and 15 days. We simulated all the scenarios mentioned in the previous slides and calculated the average cost of the CZ3100 ticket cost for each strategy. The optimal strategy comes out to be the third type with an X value of 25. Compared to the baseline model, it helps an average customer to save up to 267 RMB in each purchase, which is equivalent to 17.5% of the original cost. This is a visualization of the optimal strategy. To conclude this part, first, we successfully proved the hypothesis wrong that one may delay his or her purchase behavior to catch lower price. Second, we found an effective strategy for purchasing tickets for CZ3100, this specific air route, and it helps save up to 17.5% of airfare on average. Last but not least, the research methodology we've experimented is also applicable to analysis of other air routes. That is to say, customers can always perform similar analysis to save money.